According to the National Electrical Code, specifically Section 250.118, armored cable, often referred to as AC cable or BX cable, can be used as an equipment grounding conductor. This allowance is contingent upon meeting certain requirements outlined in the code to ensure that the cable provides a reliable and low-impedance ground fault current path. When dealing with receptacles in a system utilizing AC cable as the equipment ground, a bonding jumper is required. This bonding jumper serves to connect the outlet box, which is presumably metal, to the grounding screw on the receptacle. The purpose of this jumper is to create a direct and low resistance path for fault current to flow back to the service panel in the event of a ground fault. This is crucial for proper operation of overcurrent protective devices such as circuit breakers or fuses, which will trip and energize the circuit in the event of a fault. For light fixtures, the requirement for bonding jumpers is slightly different. Typically, bonding jumpers are not required for light fixtures if the metal frame of the fixture is already in direct contact with the AC cable's equipment grounding conductor. This means that the point where the fixture is mounted or connected to the electrical box provides a sufficient ground connection. However, it is always a good practice to verify that the fixture is indeed properly grounded. This can be done using a multimeter to measure the resistance between the fixture's metal frame and a known ground point. A low resistance reading indicates a good ground connection. One of the most critical aspects of using AC cable as an equipment ground is ensuring the continuity of the grounding conductor throughout the entire circuit. This means that all connections and splices within the circuit must be carefully inspected to ensure that the ground path is intact and unbroken. Loose connections, corroded terminals, or improperly made splices can compromise the effectiveness of the equipment grounding conductor, increasing the risk of electrical shock or fire. When working with older installations, it is especially important to pay close attention to the condition of the AC cable and its connections. Over time, the cable's armor can become damaged or corroded, which can reduce its ability to effectively carry fault current. It is also important to ensure that the connectors used to terminate the AC cable are properly installed and tightened to maintain a secure and reliable ground connection. As an additional safety measure, consider installing residual current devices, also known as RCD. These devices provide an extra layer of protection against electrical shock hazards by monitoring the balance between the current flowing through the hot and neutral conductors of a circuit. If an imbalance is detected, which could indicate a ground fault, the RCD will trip and energize the circuit very quickly, reducing the risk of injury. RCD are particularly useful in areas where there is a higher risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. They can be installed as either circuit breakers in the main electrical panel or as receptacle-type devices that replace standard electrical outlets. It's crucial to understand that while AC cable can serve as an equipment ground under the NEC, adherence to proper installation techniques and verification of grounding continuity are paramount. Moreover, incorporating RCD significantly enhances electrical safety by providing rapid fault detection and circuit interruption. Always consult with a qualified electrician to ensure that all electrical work is performed in accordance with local codes and regulations. Firstly, always ensure that you're working in an energized state. This involves turning off the circuit breaker that feeds the circuit you are working on. Before beginning any work, use a voltage tester to confirm that the power is indeed off. Secondly, inspect the AC cable for any signs of damage or corrosion. Look for cuts, abrasions, or rust on the cable's armor. If the cable is damaged, it should be replaced. Thirdly, when making connections to the AC cable, use the appropriate connectors. These connectors are designed to provide a secure and reliable connection to the cable's armor, ensuring good electrical conductivity. Fourthly, when installing receptacles, make sure that the bonding jumper is properly connected between the outlet box and the receptacle's grounding screw. This jumper should be made of copper or other conductive material and should be sized appropriately for the circuit's amperage. Fifthly, when installing light fixtures, verify that the fixture's metal frame is in direct contact with the AC cable's equipment grounding conductor. If necessary, use the bonding jumper to ensure a good ground connection. Sixthly, test the ground continuity of the circuit using a multimeter. Measure the resistance between the grounding screw and the receptacle and a known ground point, such as the metal enclosure of the service panel. A low resistance reading indicates a good ground connection. Seventhly, consider installing RCD to provide an additional layer of protection against electrical shock hazards. These devices can be installed as either circuit breakers in the main electrical panel or as receptacle-type devices that replace standard electrical outlets. Eighthly, always follow the manufacturer's instructions when installing electrical components. This will help to ensure that the components are installed correctly and that they will function properly. Ninthly, after completing the electrical work, inspect it carefully to ensure that everything is installed correctly and that there are no loose connections or exposed wires. Tenthly, before restoring power to the circuit, double-check that all tools and materials have been removed from the work area. The equipment grounding conductor plays a crucial role in electrical safety. It provides a lower impedance path for fault current to flow back to the source, allowing overcurrent protective devices to quickly trip and energize the circuit in the event of a ground fault. Without a proper equipment grounding conductor, fault current may not be able to flow back to the source quickly enough, which can result in a dangerous buildup of voltage on metal parts of electrical equipment. This voltage can pose a serious shock hazard to anyone who comes into contact with the equipment. The NEC provides specific requirements for the size and installation of equipment grounding conductors. These requirements are designed to ensure that the grounding conductor is capable of safely carrying the maximum fault current that could occur in the circuit. When using AC cable as an equipment grounding conductor, it is important to ensure that the cable is properly sized for the circuit's amperage. The NEC provides tables that specify the minimum size of equipment grounding conductors based on the size of the overcurrent protective device protecting the circuit. In addition to ensuring that the equipment grounding conductor is properly sized, it is also important to ensure that it is properly installed. This means making sure that all connections are tight and that the grounding conductor is protected from damage. When making connections to the equipment grounding conductor, use the appropriate connectors. These connectors are designed to provide a secure and reliable connection, ensuring good electrical conductivity. When routing the equipment grounding conductor, avoid sharp bends or kinks, as these can damage the conductor and reduce its ability to carry fault current. Also, protect the grounding conductor from physical damage by routing it in conduit or other protective raceway. Regular inspection and testing of the equipment grounding system are essential to ensure its continued effectiveness. Over time, connections can loosen, corrosion can occur, and the grounding conductor can become damaged. Regular inspections can help to identify these problems before they lead to a safety hazard. Testing the ground continuity of the system can also help to ensure that the grounding conductor is still providing a low impedance path for fault current to flow back to the source. If problems are found during inspection or testing, they should be corrected immediately. This may involve tightening connections, replacing corroded parts, or repairing damaged conductors. By maintaining a proper equipment grounding system, you can help to protect yourself and others from the hazards of electrical shock and fire. Remember that electrical work can be dangerous and should only be performed by qualified individuals who are familiar with the NEC and local codes. Always follow proper safety procedures and use appropriate personal protective equipment when working with electricity. If you are not comfortable performing electrical work yourself, hire a qualified electrician to do the job. Consider using a ground fault circuit interrupter, also known as a GFCI, especially in locations that may be damp or wet. A GFCI is a type of RCD, residual current device, that protects people from electric shock. It works by monitoring the current flowing in the hot and neutral wires of a circuit. If there is a difference of more than a few milliamperes between the two, the GFCI will trip and quickly cut off the power. This can happen if someone is touching a live wire and current is flowing through their body to ground. GFCIs are commonly used in bathrooms, kitchens, and outdoor outlets, where there is a higher risk of electric shock. You can also install a GFCI circuit breaker in your electrical panel to protect the entire circuit. When working with electrical circuits, it's important to use the right tools. Insulated tools are a must, as they provide a layer of protection against electric shock. These tools have a non-conductive coating on the handles that prevents electricity from flowing through them to your body. You should also use a voltage tester to check if a circuit is live before you start working on it. A voltage tester is a simple device that can detect the presence of electricity in a wire or outlet. It's important to choose a voltage tester that is rated for the voltage of the circuits you'll be working on. Always wear safety glasses when working with electrical circuits. This will protect your eyes from flying debris or sparks. You should also wear gloves to protect your hands from cuts and abrasions. If you're working in a damp or wet environment, wear rubber gloves to protect yourself from electric shock. It's important to keep your work area clean and organized when working with electrical circuits. This will help you to avoid accidents and make it easier to find the tools and materials you need. Keep all flammable materials away from the work area, as sparks from electrical circuits can easily ignite them.